Hi, everybody. It is week 14, and this week we are going to continue our discussion of solutions, and we're going to begin talking about some of the most important solutions in all of chemistry, acids and bases. So here's what we've been doing recently. We've been talking about water, that universal solvent, some of the properties that water strongly exhibits, like cohesion, adhesion, capillary action. We've defined solutions, suspensions, colloids. We've talked about emulsions, those wild and crazy mixtures of oily and watery compounds, and how are they held together by emulsifying agents. We talked about the fact that like dissolves like. You need covalent compounds to dissolve covalent compounds and ionic compounds to dissolve ionic compounds. We mentioned dissociation, the fact that if you take a ionic compound in solution, it breaks into ions, and that is a constant process of breaking into ions, coming back together, and breaking back into ions. Well, this week, as we continue with our discussion of solutions, we are going to talk about what affects the rate of dissolving. How quickly do things dissolve? And then we're going to spend a lot of time talking about how do you express how strong a solution is. If a solution is very, very strong, or if a solution is very, very weak. And the difference can be if something is tasty or if something is deadly. And that's very important. So there's lots of different kinds of concentration notation that can be used. We're going to discuss those. And we are going to hold on to your hats. I know it's not your favorite for some of you. We're going to do some math, but it's pretty easy. It's all just percentages, and percentages are just division multiplied by 100. And that's what we're going to do for all these concentrations. Then the last thing this week, we're going to start the important topic of acids and bases. And acids and bases, we're going to start this week, and that's going to carry us to the end of our course. But to begin with, for the rest of this little talk, we're going to talk about how do you increase the rate at which something dissolves. Now, any of you who have ever tried to mix up Kool-Aid or Tang or powdered lemonade or iced tea or any of these things, know that you have to mix them up a lot. They don't dissolve right away. Sometimes it seems like you stir and stir and stir and stir, and there's a whole bunch of things that influence how fast things dissolve. So let's talk about this and what's actually chemically going on when this happens. Well, one of the things that speeds up the rate of dissolving is to increase surface area. If you put a sugar cube into a container of water versus granulated sugar, well, your common sense tells you granulated sugar is going to dissolve faster than the sugar cube. But actually, in a chemical method, what's going on? Well, dissolving means that the water molecules have to surround and remove the individual pieces of sugar. The picture I have here actually happens to be salt molecules, not sugar, but it does totally illustrate what's happening. So in order to totally hydrate this crystal or this solid, that is the solute, we have to allow the water to get at the powder that's being dissolved. If you have a solid, they have to remove the outside layer and then remove the next layer and then remove the next layer. If something is if something is already in granules and in small pieces, this is going to be much faster than if it is in clumps. And I know you've experienced this when making cookies or trying to dissolve Kool-Aid or something like that. So increased surface area is going to increase the rate of dissolving. And it all is about getting those water molecules next to the thing that is being dissolved. So common sense, which I kind of like. The next thing that increases the rate of dissolving is stirring. Again, from common life experience, I'm sure you have had this experience. we have to get those water molecules next to the thing that we are trying to dissolve, assuming we're dissolving in water. Now, these rules apply whether you're dissolving in water or alcohol or oil or any solvent. Any solvent, the rules are the same, but I mention water a lot because that's what you and I have had a lot of experience with. We have to allow the molecules to have continuous contact with the solute that we are trying to dissolve. And what stirring is going to do, it is constantly supplying fresh molecules, bringing them close to the surface that we are dissolving. If we allow this to happen randomly, it is going to be slower. And so by stirring, we are bringing those fresh molecules in at a nice, fast rate. And so stirring is going to make that reaction rate or that dissolving rate faster and faster. Temperature. Temperature also is going to increase that rate of dissolving. And it is not the same for every substance that we dissolve. In general, here's what's actually going on. We've talked about the fact that hotter means higher kinetic energy, means that the molecules are actually vibrating faster and faster and faster as they get hotter. So more energy per molecule, more speed, more motion. That also means more collisions per unit time, more collisions per second. That means the molecules are going to be zipping in and out of that solution and doing that dissolving at a quicker speed. Hot water dissolves things faster than cold water. And from cooking experience, you've probably seen that occur. That is also one of the reasons why hot water is going to be better in your laundry at removing stains than cold water. Now, cold water can set some enzyme stains like blood, but hot water is going to remove most stains faster. Why? You're going to have more collisions, and more collisions are going to mean a faster reaction rate. But different compounds are going to respond differently to that rate of reaction. And I'm not going to ask you to interpret solubility curves, but I want you to have seen one and see what it means. Now, a illustration like this is in every chemistry book on planet Earth. And if we look at sodium chloride, plain old ordinary table salt, sodium chloride right here, temperature is here on the x-axis. And as temperature goes up, this y-axis says grams of solute per 100 grams of water. So as temperature goes up, look at what happens to sodium chloride. The amount that can be dissolved with increased temperature is almost no change. And that is because the sodium chloride bond between the sodium and the chlorine is so strong that an increased kinetic energy in the water does not make much of a change at all. But if you get something like potassium nitrate has this blue curve right here. And if you look at this curve for potassium nitrate, a small change in temperature means a massive change in solubility. You heat it up a little bit and lots more potassium nitrate can dissolve. So every compound is different. Sodium nitrate, potassium iodide, hydrogen chloride, actually for HCl, actually has a reverse solubility curve you can see right here. So every compound is going to be a little bit different, and that is why chemists study these things. We have a very small, this is a basic chemistry class. We're not going to go into it in great depths, but I do want you to know, in general, hotter means more increased dissolving rate for most things. Last thing we're going to talk about is just something that's kind of fun, because most of us in our lifetime have drunk soda pop. And you probably have noticed that when you first open a can of soda, it is full of a lot of gas and it is full of a lot of bubbles. Well, Henry's law states that when something is under high pressure, it will hold lots of gas. And Henry's law, he discovered that when you have a liquid and that pressure goes down to low pressure, a liquid will hold very little gas. So what happens is after you have opened the soda pop, let it sit around overnight. Maybe you left your pop can on the kitchen counter overnight because you didn't drink the whole thing. It goes flat. And that is because of the fact that without that pressure holding those gas bubbles in, the gas bubbles evaporate, they come out, and your pop goes flat. There is actually a law of chemistry to explain why, without being contained in a pressurized container, your bubbles go out of your favorite bubbly beverage. All right, that will do for this time, and we'll see you later. Bye-bye.